Yeah, exactly. I had to ask Jamie nicely to chew out the IT department. Then she did it. Okay, so the next thing we have to talk about is temperature. And I'm not going to say a lot about this, but I just want to make you aware of the pitfall that's sort of available with temperature. I started this right. Yes. So there's one tricky thing with temperature. And you don't get this with other types of unit conversions. And it all comes from the fact that different temperature scales have different zeros. Well, not all of them do, but Fahrenheit and Celsius, which are common units for temperature, zero isn't at the same place. You don't get that with other things, like zero force in newtons is the same as zero force in pounds, or 0 meters is the same as 0 inches. But that's not true with Fahrenheit and Celsius. So since degrees Fahrenheit and degrees Celsius have their zeros at different places, conversions for changes in temperature are done differently than conversions of actual temperature at an instant. Okay, that's the heart of the problem. So you convert changes in temperature or temperature differences differently than you convert instantaneous temperatures. Okay, so if something's length is 2 meters, you use a certain conversion to turn that into inches or feet or whatever, okay? If instead of talking about this thing has a length of 2 meters, you say that this thing's length has changed by 2 meters, or there's been a change in position of 2 meters or something. To convert that to feet or inches is exactly the same as it was in the just instantaneous case. But with temperatures, it's not, and it's all because of the fact that the zeros are in different places. So the 4 temperature scales that we're going to deal with. So our 4 temperature scales, or our 4 units for temperature, are Fahrenheit, Celsius, and then Rankine, and Rankine uses the Fahrenheit scale, but it has its zero at absolute zero. So zero in Rankine is absolute zero. And then the last one is Kelvin. That's actually the one we'll use the most. 459.67, negative 459.67 Fahrenheit is absolute zero. And Kelvin is the Celsius scale, but 0 Kelvin is absolute zero. So 0 Kelvin is absolute zero. So what all this means is, so notice, this is the thing that you have to remember. When you see something with a temperature, you just have to be clear to yourself. Ask yourself, am I talking about a difference in temperatures, like a change, or am I talking about an instantaneous temperature? If you don't know that, you can't deal with it, okay? So first, you need to know if you're dealing with an instantaneous temperature or a difference in temperatures. Or a temperature difference. Okay, so for instantaneous temperatures, the conversions work like this. Temperature in degrees Fahrenheit is equal to the temperature in the Rankine scale, degrees Rankine, minus 459.67. You can, on all these, I often just round to the nearest degree because it's a pretty small round off error that you get from that. Temperature Celsius, so temperature in degrees Celsius is equal to the temperature in the Kelvin scale. I don't know why you never write the degree sign for Kelvin, but that's just how it is. Minus 273.15. And the temperature in degrees Fahrenheit is the temperature, sorry, we have to multiply this because Fahrenheit and Celsius have different scales. So this is equal to 9/5 times the temperature in degrees Celsius plus 32. Okay, so with those, you can go from any one of those four to the other ones. So that's if you're talking about instantaneous temperatures, like what's the temperature outside? That's how, right now, that's how you calculate that. If you're talking about temperature difference conversions, so it says something about this gas started at, you know, a certain temperature and then its temperature rose 46 degrees. Then you're talking about a difference in temperatures. So temperature difference conversions the change in temperature, so I'm using that change symbol to remind you that we're talking about differences, in Fahrenheit is the same thing as the change in temperature in the Rankine scale. Okay, so if the temperature starts at something and then goes up 2 degrees Fahrenheit, it also goes up 2 degrees Rankine. You don't use that additive part of the conversion. The change in temperature in degrees Celsius is the same as the change in temperature in Kelvin. And the change in temperature in Fahrenheit is 9/5 the change in temperature in Celsius, degrees Celsius. Okay. So if you're talking about changes, you drop all those additive parts. It makes sense if you think about it, because a change in temperature, you're subtracting 2 temperatures, and the first one has that additive part, and the second has the additive part, and so when you subtract, they cancel each other. Okay. So why don't you have to deal with this with any other types of units, with any other quantity? Because of the fact that these have different 0 points. It causes the headaches. Okay. Any questions about that? Yes? What's the cause of them having different? Because when people defined those scales, nobody knew what absolute 0 was yet. You know, like 0 length of something is really like obvious, you know? Right. But 0 temperature wasn't obvious until, you know, wasn't obvious. Like people had to learn a lot of physics before they're like, oh, there actually is such a sensible place to put the 0, you know? But so Fahrenheit 0 doesn't mean anything particularly. Celsius 0 is the freezing point of water at atmospheric pressure. So Celsius sort of, they at least tried to choose something that made some sense. Fahrenheit, they're just like, oh, it's really cool that they call that 0 or whatever. I don't know how they chose, you know. Yeah. But, you know, it turns out that absolute 0 is a very sensible place to put 0 for temperature. And in all the equations that we're going to use that use an instantaneous temperature, you have to use one of those scales with 0 at absolute 0. Okay, so like the ideal gas law, you can write that in Kelvin. We'll use that more often, or you can do it in Rankine, but you can't do it in Fahrenheit or Celsius. Okay, so next let's talk a little bit about pressure. This is going to be a big thing for us, and actually it's an important idea in fluid dynamics. So you know, pressure will come up a lot in your future classes. So let's talk a little bit about what it is and what it isn't. Pressure can be applicable to solids, but mostly it's applicable for fluids. So let's say that it's mainly a useful concept for fluids. And fluids are just things that flow, so fluids include liquids and gases. Pressure doesn't start with an F. Pressure is a force per area that the fluid applies perpendicularly to every surface. to every boundary. Okay. So for example, if you have, let's say this is a cross section of a cylindrical tank holding a gas. So there's gas on the inside, and the gas pressure applies a force per area perpendicular to the surface there, perpendicular to the surface there, there, and so everywhere it's exactly normal to that surface. Okay. And what it is so it's caused by repeated collisions of the fluid molecules with the surface, with the boundary. So repeated collisions of fluid molecules with the boundary. And what that means is that, so the pressure is always toward the boundary, away from the fluid. Well, let me make one. So the pressure, so this right here is the pressure applied by the fluid. So this is applied to the boundary by the fluid. If you want to talk about the pressure that the boundary applies to the fluid, then Newton's third law says it switches directions. Okay, so what this means is, notice, there's no such thing as suction. If you're just talking about collisions of molecules with a boundary, okay, all it can do is push things away, okay? So all pressure can do is push. So there's no such thing as suction. So what happens in cases where you sort of think of differences in pressure causing suction? Like imagine like when in a movie when the door of an airplane gets knocked out and it looks like everyone gets sucked out of the airplane, okay? What's really happening is you just have two pressures, and wherever there's a high pressure, if they get to all of a sudden interact with each other, all of those molecules in the high pressure area want to equalize into the low pressure. So there's a very high pressure inside the airplane because they're keeping the pressure so you can breathe in there. And when the door breaks out, that pressure, the high pressure on the inside sends the air rushing out into the lower pressure outside. So you're not being sucked out, you're being blown out by the pressure trying to escape, okay? So there's no such thing as suction, there's only different pressures pushing against each other. And the effect of that is that high pressure gas wants to move into lower pressure. You have a question? In practice, you can get so close to zero pressure that I guess maybe for practical purposes, I guess I would say no. But it's possible that to actually get to zero pressure, you'd have to get to absolute zero. But yeah, I mean, there's all sorts of places where with pumps they can get the pressure down very, very, very close to. Yes.
I was going to just add, like, isn't the lowest pressure tube like the large vacuum collector?
I don't know that. I don't know.
I think because they use like an ultra high vacuum system for that whole thing.
Okay.
Like that would accelerate the particles. Get a really low pressure. We learned about it in the vacuum tank.
Oh yeah, cool. I know I've seen a video where I showed this in Physics 1, where there's this gigantic like building that they can suck almost all the air out of, enough of the air that you don't have any effective air resistance in it, and they use it for space applications and stuff. But there's a video of this physicist convinces them to suck all the air out just to drop I think it was a feather and a bowling ball, you know, and they suck out enough that there's no collisions with air molecules. The two fall exactly together. The feather hits the ground and bounces way up into the air. It's really cool looking, but it's a very expensive process, but basically zero pressure. Okay, so there's no such thing as suction, only different pressures pushing against each other, and high pressure gas moves to a lower pressure. Have you ever, like, so this is kind of a different aspect of being in an airplane, so I don't want this to be confusing, but so when you're in an airplane at 30,000 feet, the pressure in the airplane is very high compared to the pressure outside the airplane, and that's why if the door blows off, everybody gets blown towards the door. But the pressure in the airplane at 30,000 feet is still lower than the pressure is at ground level. Just to save money and stuff, they could crank it all the way up, but people aren't exercising or anything. So I think they pressurize airplanes to the equivalent of about 10,000 feet of altitude, which is pretty high, you know. So that's the pressure inside an airplane is quite a bit lower than it is at ground at sea level. So have you ever noticed that when they bring the snacks around, if you get like a bag of potato chips, it's inflated on an airplane? So what's going on is the potato chips are packaged at sea level, and at sea level you have atmospheric pressure pushing out, and atmospheric pressure pushing out, atmospheric pressure pushing in, and it's a tie, so it just stays, you know, the way that it was when you sealed it up. Then when you fly this in an airplane and the inside is at a lower pressure than atmospheric, none of that air inside can escape. So you still have 1 atmosphere of pressure pushing out, but now you have something lower pushing in. And now this pressure on the inside is somewhat winning the battle with the stuff on the outside, and the bag inflates. And if you make the pressure on the outside low enough, the bag will explode. And it used to be the case that when you used to, where you put your baggage on an airplane was not pressurized. And so if you forgot to take your shaving cream or whatever out of your bag, when you got up to 30,000 feet, your shaving cream would, you'd take out your bag and it would be everywhere. Because at that point you have the pressure at 30,000 feet fighting against atmospheric pressure, and that's way too low, and the atmospheric pressure just blows the whole thing apart. Yes? No, that's just because they think you'll make a bomb out of it. Yeah. So, I mean, like, okay, so if you have a fluid, so a gas or a liquid, that's continuous, and at rest, okay, those are the 2 requirements, then, and let me draw, so this is just, you know, any arbitrary shape. Right inside here is the fluid. What? Continuous means that there's nothing keeping parts of that fluid separate from each other. And so let's call this 0.1. Is that, no, let's call that 0.2 actually, just the way I'm, and that's at a height 2. And let's call this 0.1, and it's at height 1. And that means that this distance is what I'm going to call h. That's like the difference in height. And the difference in pressures, so pressure 1 minus pressure 2 is equal to the density of the fluid times 9.81 meters per second squared times h. So this P1 is the lower point, and the P2 is the higher point. Yep. Yeah. For a liquid, it's usually easy because liquids are usually almost completely incompressible. So But if you're looking up the density of air, you can't just look up the density of air. That all depends on a bunch of other stuff. Okay, so that explains why, you know, as you dive down in water, your ears start to hurt. You know, the pressure pushing in on you is, you know, the density of, you know, starts at atmospheric pressure and then gets bigger as you descend by the density of water is 1,000 kilograms per meter cubed times 9.81 meters per second squared times the height. So you can just use that to measure how much the pressure is increased as you descend. No, it's positive. So the 1 is the lower. In that picture, yeah, it's always set up so that the lower pressure. No. Yes, thank you. These should be switched. Oh, okay. This is, I get it now. This is the lower height, but the higher pressure. This is the high height. And the lower pressure. Okay, I think that's pretty much all I want to say about that. So when you, so if you dive down 15 feet underwater, your ears hurt because there's an increased pressure on the outside. And then if you, hold your nose and blow air through your eardrums or whatever you do, it equalizes the pressure. Okay, it lets the high pressure from the outside equalize your sinuses. And then you have an equal fight between the pressure on the inside and the pressure on the outside, and it doesn't hurt anymore. So that's what scuba divers do or whatever. Oh, yep. That is, I think as the pressure gets, I can't remember. It's something about like you change the pressure and nitrogen starts to basically boil, and so the change in so yeah, it does something to the acidity of the blood because all of a sudden the nitrogen changes in some way. Yeah. Okay, so 2 questions, just to make sure you understand this idea, because this idea is going to come up from time to time. All right, so say that you have like a inner tube in a bike tire. Okay, so there's the valve, and there's a pressure here, and an atmospheric pressure out here. Okay, and so at this point and this point, those two are at the same height. But P is greater than atmospheric pressure. How can that be according to this rule? That's right. the outside of the inner tube is keeping those two gases from being continuous. And if you pop the inner tube, then the inside goes to atmospheric pressure quickly. And then the equivalent other question, you probably know the answer to this without me even drawing anything, but so if you have a fluid flowing through a shape like this, so the fluid is moving this way, you can think of this as air. You have a low pressure there. You have a high pressure there. And then you return to a low pressure there. How can that be? Those are all the same height. And in this case, the fluid is all continuous. But yep. Well, I just want you to think of the two requirements here. Okay, so it's just that in that case, since this fluid is moving through that tube, through that tunnel, it's not at rest. Okay. So in order to use this pressure rule, you have to keep those two requirements in your head. You know, they're wildly, there are things that just totally don't obey this law if you ignore the requirements for using this equation. Okay. There are two main ways to measure pressure. The first one is a manometer, a manometer. And that's useful for measuring pressure inside an enclosure. In order to use this, you need to know the atmospheric pressure. And it looks something like this. So if this bulb is the enclosure that you're trying to measure the pressure of, you have the enclosure, and it's connected to a glass tube that makes this U shape. And then in the tube is some kind of liquid. What you're trying to measure is the pressure at the enclosed part of the liquid. And you're trying to come up with this pressure P. you know the atmospheric pressure, and that's the pressure here. And if all this stuff is at rest, and that liquid is continuous, we can use the pressure relationship that says P minus atmospheric pressure is equal to rho GH. This rho is the density of the liquid. And then the H is this. Any questions about that? Yeah. Yeah, it doesn't really matter. I mean, you just need the, if you, it needs to go down and then go back up, that's all. And we're assuming that the density, the density of air at atmospheric pressure is around 1 kilogram per cubic meter. The density of water is 1,000. So if you have a liquid here and a gas here, whether it drops down a small amount there doesn't even make enough of a difference to worry about because the density of the gas is so low compared to the liquid. I suppose that could be different if you have a very high pressure. No, you don't need to do that. And actually, we could start out by drawing a free body diagram and going through the physics of it, and eventually we come back to this equation. So we'll skip it. But yeah, we don't have to know anything about that, and actually, this shape could be wavy or whatever, as long as it's continuous and still, that equation works. No, it doesn't. Any other questions about manometer? The other way to measure pressure is the way that you measure the atmospheric pressure. That's a barometer. So this is to measure the pressure of the atmosphere. And this is what that looks like. You have a tube like this that's enclosed at the top. And it drops down into a vessel. So this thing, this is a cross section basically. So this is like a round shape, square cross sectional shape or whatever. And you have a liquid in here. So this is a liquid. And the liquid rises some distance up the tube. So that's the liquid. And you want to choose a liquid that that is going to have a very low vapor pressure in here. Some liquid with the temperature and atmospheric pressure that you're using, well, I guess that temperature that you have, a lot of the liquid would turn into gas, and then that gas would exert some pressure here, okay? But other things are they're not trying to escape the liquid, not a lot of that liquid is turning into gas, and so there's very low pressure pushing back this way. The most obvious one is mercury. So this is a liquid that has close to zero vapor pressure at this temperature. Like mercury. Okay, so right here, the idea is that this liquid is all exposed to the atmospheric air. Okay, so what's the pressure right there? The pressure here is the atmospheric pressure. That's what we're trying to calculate. What's the pressure here inside the tube? Yep. The idea is that we used a liquid that's going to make that pressure. So we'll call this P, and it's about equal to 0 if we use the right liquid. And the difference in height is this H. And so the atmospheric pressure minus that pressure P is equal to rho G H. This rho is the density of the liquid. This P, we're going to assume that that goes away. And so there's your calculation of the atmospheric pressure.
And the pressure of the atmospheric pressure, that red dot you have there, is that just because it's in contact with the atmosphere?
Yep,
Okay.
that's right. So anything so at any interface between a liquid or a gas, if the thing is still and they're touching each other, at that location, the pressure has to be the same. Okay. Okay, so let's do an example that combines both of these things. Let's say we want to know the pressure inside this vessel. And let's say that this is, let's say that this is water. And water has a density of 1,000 kilograms per meters cubed. And in order to do this calculation, we need to know the atmospheric pressure. So let's say that on the table next to it, we have a barometer.
Is that atmospheric pressure?
760, that's in some kind of mercury unit. Okay. Well, it changes, you know, like that's how you get different barometric pressure at different, you know, with different weather and also at different altitudes and different whatever, you know, it's different. So you need to know for your specific thing. But yeah, what you're talking about is just sort of like the usual average sea level. Yeah, that's right. Yeah, exactly. So at altitude, you have a much lower pressure, you know. You know, like when people get, so altitude sickness is like when mountain climbers in the Himalayas, tall mountains, the air pressure gets too low and they're not getting enough oxygen. One of the ways that they treat that is they put someone inside a giant like enclosed sleeping bag with a pump attached to it, and then they just pump air into this sleeping bag to increase the pressure that the person is in so that they can get more oxygen per breath. I don't know what that had to do with anything. It just made me think of it. Okay, so, and this thing, let's say that this liquid is mercury. And mercury has a density of, it's much higher, 13,690 kilograms per meters cubed. And let's say that this distance is measured to be 0.55 meters. And this distance is measured to be 0.8 meters. And we want to know what's the pressure P. Well, we want to use the manometer equation to calculate that enclosed pressure P. So from the manometer, we know that P minus the atmospheric pressure is equal to the density of water times 9.81 times the height of that column of water, which is 0.8, and that comes out to be 7848 we could figure out that those units, but it's SI units, so I guess it has to be in pressure. So this is in SI units. You know, pressure is always a force per area, so this has to be newtons per meter squared. And the last thing we have to do is figure out what the atmospheric pressure is. Or I can rewrite this as the pressure that we're trying to find is equal to 7848 plus the atmospheric pressure. And now we use the barometer equation. And that equation says the atmospheric pressure is equal to the density of that liquid. So now we're talking about the mercury, 13,690. Times 9.81. I usually just put all of these in SI units for every calculation, and then you don't really have to worry about what matches with what. And then the height for the barometer was 0.55, was it? And so in this case, the atmospheric pressure is 73,864 pascals. How high is that compared to like normal everyday pressure? Yeah. Yep. So standard atmospheric pressure is about 101,000 pascals. So that's really low. You know, that would be at like a really high altitude, or you know, some kind of, well, I guess weather conditions would never make that much of a difference. But let's say really high altitude. Yeah, but not all the time. You know, it fluctuates from day to day. But yeah, that's sort of like the average sea level pressure in pascals. And so now we can say, finally, you know, take this and combine them. And we know that the pressure in that enclosure is 7848 plus 73,864. Can someone tell me what that is? I don't have that calculated. 81,712 pascals. Any questions about that?
So that total there, that's the total pressure for both the manometer and the barometer? It seems like they're two different figures.
Yeah, that is just this pressure P in the manometer. Okay, so that's what we're trying to find is the pressure of that gas in that enclosure, just that pressure P. And then, but to find that, if you look at that manometer equation, it has the atmospheric pressure in it. So before we can figure out what that pressure is that we're looking for, we have to use the barometer to calculate the atmospheric pressure.
Oh.
And plug that in here, and that'll give us the pressure inside the bulb enclosure.
No, I mean, it just seemed like there were two different applications,
Yeah.
two different liquids.
That's right.
And at the end of the day, we're still one company.
Oh, okay. So the answer from the barometer was to calculate the atmospheric pressure, and that answer was this, 73,064.
Right, I'm talking about that 81,000.
Yeah. So
I'm guessing.
okay. So we're just we're just trying to calculate the pressure there. But the equation for the manometer for this has atmospheric pressure in it, so we have to take a little side trip to figure out the atmospheric pressure and then plug it in.
Okay, I got it. Thank you.
Yeah. Any other questions about that? Mm-hmm.
Newton per meter squared, is that Pascal?
That's a Pascal. That's right. Yep. Yeah, I don't know why I wrote that here. This, I could just write this as Pascals. Any other questions? Okay, let's do one where so this, I think I asked a few questions like this on the assignment that I'm going to give you for this class. So let's do another example. So let's say that we have this box with a valve on it that so you can inflate it with air. So you have this hollow box. It's a cube, so all of these side lengths are the same. And let's say that the side lengths are 0.35 meters. So this is a hollow cube. And let's say that we use a pump to increase the pressure inside. So inside this cube, to a gauge pressure of 100 psi. And if you convert that, that's equal to about 689,000 pascals. You know, like a racing bicycle, that's about somewhere around there is the pressure in the tire. And we want to know what's the total force on one face. You know, what's the, let's say, what's the net force on a single face of this cube? Okay, well, first of all, gauge pressure is anytime you're using a pump to measure a pressure, you're measuring the difference in pressure between the atmospheric pressure and the pressure of the thing that you're using. So if you pump your bike tire up to 100 psi, that's not the absolute pressure of that gas. What you're seeing is that inside the tire is 100 psi higher pressure than the atmosphere. Okay. So the absolute pressure is the gauge pressure plus the atmospheric pressure. In this class, the pressure that we want is always going to be the absolute pressure. So if you're given something in gauge, you always have to add the atmospheric pressure to it to get what you want. So we always want the absolute pressure in this class. You can think like if you're using the ideal gas law or something, you don't want the difference between the atmospheric pressure and what this gas is at. You want the absolute pressure of this gas. And so the absolute pressure on the inside of the box is the gauge pressure, 689,000 pascals, plus the atmospheric pressure, which is 101,000 pascals. Look at those numbers, by the way. Like, that might be sort of surprising. Atmospheric pressure is a ton of pressure, you know. If you're not taking that into account in your measurements in this way, you're very often going to be missing a pretty significant contribution. Like, think of how hard a racing, you know, a road bike tire is when it's at 100 psi. That's only 6 times as big or something as what the atmospheric pressure is. Yeah. Not because of, if the front one pops from experience, you fly off the bike because all of a sudden you can't steer. That I know.
So should I stop pumping my tires to 100 psi? It's probably like to 90, 95.
No, I mean, tires, I mean, they're made for that. Some tires are made for 120 psi. I mean, you need to pump them to whatever you have your, yeah. Yeah. Well, if you underinflate your tires, then you have a whole other set of problems. So yeah, but it's me. I mean, I love bikes and stuff, so I do it just for transportation and just sort of relaxation and stuff. I don't race. I don't. I used to when I was young, but yes, I think everyone does when they start. Yeah, I mean, you can fall in so many embarrassing ways with those things. I'm not going to get into that. But everyone looks like a fool when they start with those, I think. Exactly, right, that stuff. It's hilarious. Yeah. Okay, so let's think about, okay, so here's the cube. And let's think about this wall. Okay, I just said one, so it doesn't matter which one we're thinking about. Okay, so the area of this wall, you know, we're going to have a force coming this way from this side, from the inside of the box, and we're going to have a force coming this way from this side of the box. And each of those forces is a pressure times the area that it's being applied to. So how do we calculate the area of this wall that force is being applied to? Yeah, 0.35 squared. Nope, not to figure out those forces, although you would use that if you're trying to figure out whether this box is going to explode or not under this pressure. That's this area of the face. Yeah, let's skip that. So yeah, we'll say it's thin enough that that's going to be small. Yeah, it's a good question. That's important to know. So 0.35 squared is, I guess I don't have that. Can someone calculate that? I don't have that written here. 0.1225 meters squared. And so the force acting on the left side from the inside of the box is, this is the absolute pressure. Oh, I should calculate this. What's that, 790? And so this force here is 790 times 0.1225. And how do we calculate the force coming from the other side, from the atmosphere side? Atmospheric pressure times that same area, yep. And the atmospheric pressure is, so we have 101,000 times that area, 0.1225. And so this one comes out to be and the units are newtons because we're in SI units. And the other side comes out to be 12,372, I think. And that's newtons. And so the net force if we think of it as, we think of positive going this way, okay? So now we have to think of this in terms of directions because forces are vector properties. So we have positive 96,775 plus a force going the other way of 12,372. Okay. I'm going to leave it like that. What I have in my notes. Otherwise, I have to change my calculation. And that comes out to be a net force in this direction of positive 84,403 newtons. So each face on that box has a net force of 84,000 newtons. What's that equivalent to? Think of that as like the weight force of about 8,000 kilograms. You know, so what's 8,000 kilograms is, yeah, is close to 20,000 pounds, I guess. So each face on that box has a net outward force of 20,000 pounds trying to explode this box. And then if you're trying to figure out whether this box is going to be able to withstand it or not, you'd think about, well, how's it attached together, you know, and that's the kind of stuff that you think about in D-form. But the basic idea of this example is to figure out how to go from these pressures, the pressure here, the atmospheric pressure, how do you go from these pressures to adding them up as forces and, you know, figuring out net forces from that. And there's a few problems like that on the assignment. Anybody have any, want me to clarify anything about this approach? Okay, well, by tonight sometime, I'll get the assignment posted. And I would recommend that you try to get it done, by class on Thursday, just so that you don't start getting behind on stuff. And if we do, we're canceling it. If it says that we do, then we'll cancel it and just go to quiz 2. Yeah, we haven't said enough yet to really have a quiz. And then next time we'll get into the first law of thermodynamics.